Let me know po, Doc Marsh, if I can play the videos na po.
Okay, we'll wait around 8:35 and then we can probably start.
Okay po.
Okay na, Feb?
Okay po.
Okay, we're gonna play the intros. Good evening, everybody. Good morning.
Doc Marge.
Tapos na?
Yes po.
Okay. Okay. All right. Good morning, everybody in the Philippines, and good evening, those who are in the US. Welcome to our webinar today. And so we invited for us as our speaker today has very been kind to attend to present a seminar today. I met him. When did I meet you? About a few months ago when he came to the University of South Carolina to be a distinguished speaker. And so I thought that it would be great to invite him and share him with the PAASE community. So today we welcome Dr. Eric Daza. And so Eric, as we were just talking about, has been a biostatistician and a health data scientist for 21 years. He actually started as a biologist, which I forgot. He had his BA in neurobiology at Cornell University. And then he did an MPS in applied statistics also at Cornell University. Maybe this came from your counting of bees and beetles during your summer job. I hope so. Or maybe that inspired you. And then he got his PhD in statistics at the University of North Carolina. So Eric created Stats of One, which is a newsletter and a podcast that has been featured in Forbes and Fortune of N-on-one trials for switchback experiments, single case designs, and personal AI for digital health and medicine. He invented a patent pending method, which I think he'll talk about today, using his time series causal inference framework. Eric has been a lead DEI leader at the American Statistical Association. We actually saw him at the meeting in Portland last 1st of August. He's a Filipino-American immigrant, and he is also a trained musician. So Eric, without further ado, I know when Eric came over, we took him out to dinner, and people thought the waitress said that he was our son. So I'm like, okay, you're old enough to be my son. So Eric, welcome to PAASE. And so Eric will present his talk, which is titled Discovering Your Own Health Behavior Causal Effects Using Wearables and Apps. Eric?
Great. Thank you for the very gracious intro, Dr. Pena. And I will call you Ate Marge, not
Yes.
my older sister, not my parent. That was a
Not
fun
Lola. That's
dinner.
right.
That's no. So thanks everyone for attending. I will, oops, let me share my screen. Okay, so hopefully this works. And hopefully everyone can see my screen. Let's see.
Yeah, it's working. We see it.
Okay, great. Thank you. Just going to change my settings here. Okay. So as we said, the title is Discovering Your Own Health Behavior Causal Effects Using Wearables and Apps. There's a little grayed out subtitle here, using wearables and apps to characterize your own recurring average treatment effects. That's the more jargon way of saying what I'm going to talk about today. Okay, so the agenda is as follows. We'll leave a lot of time for question and answer throughout. I will try to monitor the chat. Oops, let me see where that is. No, for some reason I can't see where the chat went, but we'll figure that out. Okay. So first I'll explain what N of 1 trials and studies are, which is the setting that we'll be in for today. These are studies that are done in humans, in human participants, typically in the context of clinical trials or health and medicine to see if an intervention is working or if it's not. Let's see. There's the chat box. Okay. There, you'll see some grayed out parts of the agenda. I won't get to those in detail up front, but depending on the questions, we can always jump into those in more detail later on or as the talk progresses. So to make it solid, I will share a little story that I like to call I, Robot of One. If there are any sci-fi fans here, this is a play on words from Asimov's book, I, Robot, which was made into a movie with Will Smith a few decades ago. And then that story will kind of help you understand what we're talking about here and why this method is applicable. Then we'll see how we use the method that titled the talk, motor, to analyze some data to try to estimate the effect of sleep duration on step count or walking speed the next day. Not just the correlation, but possibly the effect of it. And let's see. And then if we have some more time, I can talk about another paper that I've co-written looking at different kinds of stressors, not just sleep duration. Okay, all right. So again, feel free to ask questions throughout. And Fab, if I can get your help monitoring the chat, that would be good because I can't see everybody.
Okay po.
Okay, thank you, Fab. Okay, so N of 1 trials and studies. What is an N of 1 trial? This is a guide that was published by the National Institutes of Health, in this case, the Agency for Healthcare Research Quality, AHRQ, here in the US, called An Introduction to N of 1 Trials. And it's a wonderful book, and it tells you how to design these things and what they are. So what are they? N of 1 trials in clinical medicine are multiple crossover trials, usually randomized and often blinded, conducted in a single patient. So this is where we get the name N of 1, right? N is your sample size. In this case, it's a sample of one person. But don't let that fool you. There is one person in this type of study, but they're measured multiple times. It's a multiple crossover trial. I'll explain that in a second. So as such, N of 1 trials are part of a family of what are called single case designs that have been used a lot in psychology, in education, and in social work. So if you're from one of those fields, you would know these probably as single case designs rather than N of 1 trials. So these include case descriptions. So what's working for a single patient or versus another patient. It also includes non-randomized designs where you didn't manipulate your experimental variable. It's just observed, as well as randomized designs. And here non-randomized is in bold because that is the core of the method that I will share today. So N of 1 trials are a specific form of randomized or balanced designs that are characterized by periodic switching from active treatment to placebo or between two different active treatments. The latter are called withdrawal reversal designs because you take away the treatment and then you put it back. These are also called quantitative idiographic studies. It's really just more jargon. Idiographic means individual focused. It's a word from psychology. So this might help better help you understand what I'm talking about. Here is what the trial looks like when it's designed. You have these alternating periods. Here, for example, we have two different treatment types, A and B, and this is one person. They are measured repeatedly, and in each trial period, they're given either treatment A or treatment B. This sequence can be determined in advance, or it could be randomized. Either way, it's an N of 1 trial. The important piece here is that the A's and the B's are dictated by the experimenter. So it's a design that's very well controlled. It's not just observed out in the real world. So for example, in clinical trials and in health and medicine, these designs are used to tailor treatment and dosage. Maybe I have a treatment A and a different dose B, so like 50 milligrams versus 75. And I want to see which one works better for me. So then I could run an N of 1 trial over 8 weeks like this, where in the first week I get dose A, second week I get dose B, third week I get dose B, et cetera, et cetera. And then I compare what my outcome is. Maybe it's a blood pressure medication. So I would compare my blood pressure on average during the times when I got dose A versus the times when I got dose B to see if the higher dose of the drug helped me control my blood pressure better. That's the basic idea. So these designs are also used to research or to investigate idiosyncratic conditions. So what do I mean by that? Things like migraines. Migraines are common. They have different triggers, and the triggers differ per person. This is important because, for example, for me, what if drinking a lot of coffee induces migraines, but for you, it actually helps relieve your migraines? If we put people like you and me in a randomized controlled trial, as is common in clinical trials, and half the people were like me and half were like you, we would find no effect of coffee on migraines. But that's not true, right? Half the people were helped by the coffee and half the people were hurt. So there are effects. It's just if you run an RCT, a randomized controlled trial, you would have found no average effect, and you would have concluded that coffee doesn't have an effect. Chronic pain is another one of these areas where there are different triggers for different people, and they vary in degree for what triggers their pain. And then there's irritable bowel syndrome, which is actually how I got interested in NF1 trials. One of my loved ones has irritable bowel syndrome. It's idiosyncratic, chronic, and the triggers vary from person to person a lot. So these are good for investigating recurring conditions or rare diseases. I won't talk about the rare disease case here, but rare diseases are helped by these kinds of designs because your target population is very small. And so every person counts, very much so. And so you need to consider using a different design versus an RCT. It's kind of in the nature of it being a rare disease. So here's the guide, and you can check it out online. It's really quite wonderful. It's step by step goes through the design, but also talks about funding and at least in the US, the different agencies involved. There is a growing interest these days in NF1 trials and single case designs. This is a recent publication by the Harvard Data Science Review back in 2022, where they featured NF1 trials and had, I think, like 10 or 15 different researchers contribute articles from their fields in handling NF1 designs. I won't go into this section. This is more for if you're interested in how these fit into the healthcare system here in the US. So not necessarily applicable to perhaps most of the audience. Let me just see here. Okay, yes. Well, actually, I'll go over part of this. So to illustrate the method, it involves these outcomes in the biomedical space here in the US called patient-centered outcomes. Essentially, you can think of them as surveys. So I fill out a survey about my anxiety or my depression, or about a condition. Maybe it's a high blood pressure related survey. And I have that psychometric instrument, the survey, and now I have responses. And perhaps I want to also see if a wearable device that I have, like a Fitbit, has some data there that can inform me about what, perhaps raises my blood pressure or what increases my stress in my anxiety survey. So these things are called patient-centered outcomes or patient-reported outcomes. And these are two examples of the outcomes we're going to talk about here. One is a patient-reported outcome, and one is a wearable sensor metric. So in a clinical trial, you have endpoints. Those are your outcome variables. They're called endpoints by FDA, and so the rest of the US pharma industry follows that language. An example here is migraines. And the patient-reported outcome, the PRO, or the survey, for example, would be a daily migraine diary. You could record the number of migraines you have on a given day, how bad your migraines were, and any medications you use. There are many questionnaires, surveys that are well established in the psychometrics literature for capturing these kinds of outcomes, and these are a few of them here. Oops. And now then, one of the questions we could ask is, does sleep affect my migraine number or severity? And we could measure sleep passively through a wearable sensor like a Fitbit or an Apple Watch. For example, Fitbits record your total sleep duration, as do Garmin's and Apple Watches and a number of other sensors and devices. There are PROs, patient-reported outcomes, that can correspond to these. For example, the PAASE instrument, the patient-reported outcomes measurement information system for sleep disturbance. So you could even ask the question, how well does my sensor data correlate with my survey data? But that's a separate topic. It's very important. We won't cover it today. Okay, so for this demonstration, instead of using one PRO and one wearable sensor metric, we're going to use two wearable sensor metrics. The endpoint here, the outcome that we're interested in possibly seeing the effect on, is physical activity. And in this case, we're going to measure it as steps per minute, or walking speed, also known as walking cadence, using sensor data from this Fitbit. The sleep exposure will also be measured with a Fitbit. And the question we're interested in is, what is the effect of total sleep duration? So how much I slept last night on average, what's the effect of that on my walking speed the following day, the next day? Okay, I'll pause there to see if there are any questions.
No questions po from the chat box.
Okay. Great. Okay. So time for a story. I just gave you all this background. The story is called I, Robot of One. So assume I have these two robots that I have, right? A robot A and robot B. And their job that I give them, it's very simple. You fall asleep, you wake up, and you take some steps. It's a good life for these two robots. That's all they have to do. I programmed them to follow three rules. If they slept longer tonight, then they would walk faster tomorrow. Makes sense because they got sleep, so they got rest. If they walk faster on a given day, then they would walk slower tomorrow because they, got tired, wore themselves down a bit. So they'd walk a little slower the next day. And then if they walked faster today, then they were tired, more tired, so they would sleep longer that night. These are drawn on the top right here as what's called a directed acyclic graph in the literature on causal inference. It's just a fancy phrase to say it's a graph with arrows that imply one direction only. The term DAG is also used in engineering, if any of you have engineering backgrounds. It's a common term, and here we're using it to denote causal directions. Okay, so these two robots were given an assignment. I said, hey, robots, go and for 6 months, just track yourselves using your Fitbit sensor. But what I want you to do is estimate or guess how much your sleep affected your walking speed the following day. And here we're going to dichotomize sleep as more or fewer than 7 hours as a median sleep duration. So what's highlighted in blue is the arrow, the causal arrow we're interested in. What is the effect of sleep on walking speed? So the first robot, which I've named Austin, did a randomized controlled trial, RCT. And in this setting, that's called an N of 1 trial. So Austin randomized its sleep. So you see sleep here is in purple. It randomized it every night and then recorded its walking speed the next day. That's all it did. You can see in the DAG on the top right, something very important. The arrow from the first walk variable no longer exists to sleep because Austin randomized sleep. So Austin eliminated any effect of walking the previous day. it forced itself to either sleep more or less than 7 hours through its randomized design. And this is what it recorded. So what Austin then did was it calculated its average walking speed whenever it got less than 7 hours of sleep. That's in the light gray dots here, versus more than 7 hours of sleep, which is the dark gray dots. And it calculated the average of each of those conditions, and used it to estimate what the effect of getting more sleep was versus less sleep, this difference here. So what I'm showing you in the graph on the right is literally all of those dots from the time series plot. Just move them over, and I group them by sleep amount, less than 7 hours, more than 7 hours. The dark gray band shows you the true walking speed, the true average walking speed when the robot got more than 7 hours of sleep. And the light gray band is the true walking speed when it got less than 7 hours of sleep. Remember, I programmed these robots, so that's why I know these true values. These were programmed into them. So the difference between those two is the effect of sleeping more versus sleeping less. And that's shown as this blue rectangle. The arrow within the rectangle is what Austin calculated. So you can see, it's pretty close to that blue band. So Austin was happy. So Bradford is the second robot, B. And Bradford did something different. Bradford just went out into the world and slept, woke up, walked, slept, woke up, walked. Bradford did not randomize its sleep. And then Bradford followed the same procedure as Austin. This is called a single case observational design, or NF1 observational study. And it's observational because there was no experimental manipulation. It was just observed data, which is really, that's what's typical of what you have on your sensors, right? Your wearable devices. You're not experimenting on yourself constantly, unless you're a self-tracker maybe. So Bradford did the same thing that Austin did, same procedure, took the averages of these dots under the high and low sleep conditions and took the difference. But Bradford was sad because its estimate didn't come close to the blue box, which was the true effect of sleep on walking speed. So what happened? Bradford comes to me and is sad and says, hey, Eric J., is there something I could do better here? I don't understand. So I told Bradford, look, you're a robot, and you're a learning machine, a machine learner of some sort. Why don't you fit a predictive model and see if that helps? So Bradford fits this predictive model. Remember, before they were just taking the differences between the averages, but now Bradford fits this fancy predictive model on walking speed as a function of sleep and walking speed the previous day. Goes through the procedure again, predicts out all the values, and still has the same problem. So the lesson being, just using a fancy machine learning algorithm doesn't get you a causality. It doesn't get you the effect. It's still a correlation. So we sat together and I said, hey, Bradford, when you fit your model, it's kind of like your twin. It's this model twin of yours. And let's call that model twin Hill. So the name of the model twin is Hill. What if we, instead of having you, fit another model or whatnot, what if we use your model twin and put your model twin through an NF1 trial, just like your buddy Austin? Okay, so this is why this technique is called model twin randomization, because you go and you fit your model, statistical model, machine learning model, AI predictive model, whatever you want. But you don't stop there. Instead of just predicting your outcome here under each condition of sleep, you now randomize sleep, and then you predict your outcome. You also add some noise because we want to maintain the fidelity of how much noise there is in this data. And then you compare the values between those noisy predicted outcomes. And guess what? It's pretty close. It's a pretty good estimate. Of course, you're probably saying, hey, you just cherry picked your data. I've gone through simulations to show that this holds in general, not just for this simulation. Oh, looks like there's a question. Stop here. Before I do that, remember, no robots or humans are actually randomized using this procedure. Okay, so before I go, let's see. Question, what do the robots do when they sleep? Don't you just program the robots on how many hours they sleep and walk? In which case, how can the effect of sleep be determined when it is just programmed? Oh, yes. So, great question. When the robots were programmed, it wasn't done in a deterministic way. It was done in a probabilistic way. The robots in this example are just euphemisms for simulation. So these two are simulated robots, and in the simulation, their probability of walking fast the next day is modeled as a stochastic model. So, it's like a logistic regression model, for example, um, and there's a stochastic component to that then determines whether or not they actually sleep more or less. So, great question. It's not a deterministic program; it's a stochastic program with random variation. I hope that answered your question. Any other ones? Did I miss any? No, okay. And feel free to follow up with me afterwards. There will be a link to the slides and my email as well, I think, on the PAASE website. So I'm happy to connect. Okay, so when you take that method and you apply it to real world data, this is an example of that. This is my own data, my steps per minute, and 222 days of sleep and steps data for me. When you do the standard approach, which is what Bradford did, this is what I get. I see that maybe sleeping more may have caused me to walk a little faster. It's very noisy, you can see, but on average, sleeping 7 hours is a little higher for steps per minute. When I use motor, that spurious effect, if it is actually the effect, it goes away. And what I see here is, oh, there wasn't actually an effect of sleep. So if my model that I used for motor is as close as possible to the real model that captures how sleep affects my step count and my steps per minute, it would say that there really isn't an effect of sleep. So you can see these are at least the visual differences between those two in my own data. Okay. Any other questions there? Okay. All right. Okay, so let's see how this is applied. We already just started seeing it with my own step data. You can find this in this preprints. We are almost to the point of submitting it to a journal. So hopefully it will appear in Statistics in Medicine or Statistical Methods in Medical Research. Those are the target journals. Okay, so this really just expands on what I just showed you. Here we're asking what is the average effect of sleep duration on walking speed on steps per minute. APTE here it's an acronym for a term I defined earlier in the slides that I skipped. It stands for average period treatment effect. And it's related to the average treatment effect that is talked about in RCTs and epidemiological studies. The reason the word period is in there is to emphasize this is the average treatment effect across time periods for a given person. So really, it's a time series analysis of effects. It's different from Granger causality. I go into that in detail earlier in the slides and in my own work, but I won't go into it just now. Okay, it's related to Granger causality, but it's not the same thing. Not strictly the same thing. Okay, so again, I had 222 days of my own sensor data, Fitbit 3, and I had my steps per minute. Here I took steps per minute and I transformed it into a log base 10 so that it was more symmetric and therefore analyzable using something like a standard t-test, which assumes normality. I had sleep duration coded as either 1 or 0, 1 if it was more than my median, which was 7.1 hours, and 0 below that. And then the models I fit for motor were, in the literature, it's called an outcome model. Let's see here. Don't know if I need to go through all this, but basically the model I fit was steps per minute as a function of sleep duration, high or low, and some of the lags of my steps per minute. So remember in the DAG earlier with the 2 robots, I showed you that walking speed from the day before might affect walking speed today, like I programmed the robot. And then we have other variables that are usually called exogenous variables in econometrics. Here it's the weekend. So perhaps my walking speed had a different average, over the weekend versus during the week. Reasonable assumption. The form of the model for motor, it took 2 forms. I used a generalized linear model, or GLM. It's just a fancy way of talking about your standard linear model you read about in your intro and intermediate stats textbooks. The generalized part of GLM means that it's more flexible. Linear regression is a special case, but it's the case that I use here. So essentially, just think of it as linear regression. So I have my exposure, my would-be treatment, which is sleep duration, and then past sleep the day before, and then I'm sorry, what is this? This is my sleep duration the day before. Perhaps it also affected my step count the following day. Weekends and the past step count. But so the wonderful thing about this approach is you don't have to fit a GLM. You could fit whatever predictive model you want, as long as it follows that same form where Y is predicted by some other variables. So for this demonstration, I also fit a random forest model. I predicted Y as a function of the same variables. I did this over 200 runs. So a run here is, remember that animation I showed you for Hill, the model twin? That was 1 run of motor. You randomly shuffle or permute the exposure, just like in an NF1 trial. And then you predict out the values, the outcomes with noise using that model. And then you take the averages and subtract them. So that's 1 run. I did this over 200 runs so that I could get some stable estimates rather than it just being a product of a noisy product of like this 1 run. And the results that we get look like this. So if I did just the comparison between the 2 groups, I would have seen that sleeping more increased my steps per minute by only about 0.09. It's very similar to what happens with just fitting the model and then predicting the outcomes. No randomization, but you do one more step. You fit the model and then you predict the outcomes. That's what Bradford did in the story, right? That's what Bradford did after the first part. And then when you run motor, it seems like that effect goes away. So this is what I was showing you with the graph of my own data, where it looked like under the raw approach, the no modeling approach, there may have been a difference in steps per minute between a lot of sleep and a little sleep. But then when you put it through motor, you fit the GLM, and then you predict out, you randomly shuffle the exposure, sleep duration, then you predict out the values, and the effect goes away. So really, the lesson would be there is no effect. That would be the conclusion. There is no effect of sleep duration on my walking speed, if that model is correct. But that's the reason this method is useful, because you can fit any different models. And it's up to you to decide. It's not within the scope of this talk, but the lesson is it's up to you to decide which model makes the most sense as your causal model to predict that outcome. Because if you fit a random forest here, it's like there's maybe like a little bigger effect. It's not just 0, but it's not as big as 0.09 either. So that's the lesson from using this approach. It goes past correlation, but you still have to contend with, is my model the most representative of what could really be causing my walking speed to change. Okay, and any questions there? Okay. All right. So I'll show you how myself and 2 of my co-authors then use this approach to look at other stressors and outcomes. Won't spend too much time on this, but here we had 3 participants. This is a separate paper published in 2022 called "What Possibly Affects Nighttime Heart Rate? Conclusions from N of 1 Observational Data." Again, it's found data. It's not randomized. But we used motor to try to tease out possible effects of one stressor on one outcome. The 3 participants were myself, my student Igor, and his dissertation advisor, Kate. Here, I'm just going to show you Kate's outcomes. We had 17 data types. These included wearable measured data. So again, you could get total sleep time from these devices, steps per awake time, which is like walking speed, what I've been talking about, step length, which is the total distance you walk that day divided by your step count. You can also get heart rate. That's very common. And a lot of times, health investigators are interested in how variable your heart rate is. And one measure of that is literally on a given day, what's the difference between your max and your min heart rate while you're sleeping. We also collected self-reported outcomes. So these would be the patient-reported outcomes or survey data. Here, Kate reported whether or not she socialized on a given evening, if she did yoga that day at all, if there was any exercise during the day, if she was fasting, she felt tired or sick or stressed, if it was a holiday or vacation, and if she took any short air travel. And then we had a few calendar-based variables. Holiday or vacation should actually be included here, but these included weekend, indicators for weekend, the month, the season, and the year. And these were important in order to kind of capture and therefore explain any variability that was more seasonal in the time series. Let me see here. Okay, so the ones that I will show you are these, nighttime heart rate and the difference in min-max, as well as some of these self-reported outcomes, calendar-based variables. The outcomes here, also known as dependent variables, the exposures were the independent variables. These would be the treatments or interventions we would have done if we could have randomized them. And then you have control variables that are, for example, like seasonality. Maybe you just walk slower in the wintertime. We had 11 a priori hypotheses. The ones that I'll show you here had to do with socializing as the exposure. So that's what we would have randomized. And Yoga was another one. Exercise and TSS, total sleep, already forgotten. The stress variable. Those were other exposures we looked at. X change just means expected change in the outcome. For socializing, we expected there to be an increase in the outcome of heart rate variability. For yoga, we expected to see a decrease in nighttime heart rates, exercise, also a decrease, and for stress, a decrease. Let's see here. So the results we looked at, when we used motor, we found that there was actually concordance. So the result we expected before motor, like after doing motor, matched the results without doing motor. So what that says, I'm sorry, this is like a, can we do that with this one? Increase, decrease. Oh, I'm sorry. Yes. So what this shows is that the results with the naive method are when you don't use motor. That was like my results just doing a raw comparison. And the middle column is with motor. So you can see that for some of these, you would have expected like a decrease. You would have calculated a decrease as your effect. So with H4, that was socializing. And the outcome was variability in heart rate. We expected it to decrease, but instead, if you used motor, we found that the effect was an increase, which contradicts what you would have found just using the naive method that looks at correlations. So this is just kind of further demonstration of how to use this to tease apart what the effects might be in your data. As you can see, for some of these, in the middle, for example, for hypothesis 6, using the naive method, we found an increase, and then using motor, we also found an increase. So there, the conclusion would be that if the model we used for motor is the true causal mechanism, the true causal model, then it actually is the same as if you would have just done the correlational analysis. There wouldn't have been any difference. And that's useful too, because it tells you a little bit about it tells you more about the mechanism for your outcome. Go through that. Okay. Any questions there? After this, I will show you some non-technical things, just kind of where this work is going. And then that'll be it. And then I can always dig deep into more detailed questions. But I'll stop now. Any questions?
No questions right now. No.
Okay. Okay, so let's actually skip this. Oh, yeah. So some of the extensions of this work include adding machine learning to the mix. So again, I showed you an example with using a random forest prediction model, but you could use any type of prediction model you want. Hopefully I've made clear that the motor method is after the modeling stage. So it happens after that. You already have your model, and it's just a technique to help you then see what the effect is of a given variable, and not just use the parameter estimate for that variable, or the importance metric in a random forest and check to see the differences. There's some time series extensions. So vector autoregression allows you to, look at multiple time series. In fact, the application I showed you is really just a toy example. It's not that useful, because out in the real world, you want to model multiple time series at a time, because there are multiple factors that can affect multiple outcomes. And so the more useful version of this would be a vector autoregression, where you would randomize randomize your exposure, but it would then be used to predict some of the other variables that impact your own outcome. So you'd be doing multiple predictive steps. It wouldn't just be two time series. There are signals processing extensions to this. I'd love to talk to anybody about ideas. This work is very related to control theory, which is not my area at all, but I've talked to some colleagues in that space. You could, yes, you could use modeling averages within. You could model average within period trends across periods. Period trends across periods. Yes, so this is, for example, if you're looking at, I think I can show you. I'll just show you a graph here. The idea there was this. So if you have worked with longitudinal data in the health space, you'll be familiar with what's called a spaghetti plot. And a spaghetti plot is a plot of trends in an outcome for each individual overlaid on top of each other. And they're useful because, for example, if you have one of the studies I worked on, if you have a nutritional supplement for newborns in a developing area, and you want to see if it helps the children grow, and you compare it to a standard of care, or perhaps they're not getting any nutritional supplement, you can plot the growth curve of each of those infants over time, and then see if your supplement arm's average growth curve rises faster than the other growth curve with no supplement. So that's what spaghetti plots are used for typically. Now, in this case, instead of different infants, we have the same infant measured multiple times. So let's back that up and make it just like a person. So if you have the same person measured multiple times over time, if one of those periods of time is a day, or in this case, in the graph I'm showing here, it's a time period of 3 days. You can do the same thing. You can plot their trend over a 3-day period, and then plot it again over the next 3-day period, and over the next, and overlay them, just like in a spaghetti plot. And the idea would be to see if there were differences, average differences, on the days when they had an intervention versus the days they didn't. So what I'm showing here is you have blood glucose on the y-axis. Here it's log transformed. And this was the result of an N of 1 trial that myself and 2 other co-authors did on ourselves. We deprived ourselves of sleep, not too much, but we had a sleep deprivation condition versus getting enough sleep condition. The getting enough sleep condition was called baseline, and sleep dep is the sleep dep condition. And the interesting thing here is if you plot it out like a spaghetti plot, and you fit a mixed effects model to these data, you don't necessarily see that there's a difference in average blood glucose between the 2 randomized arms for one person, but there could be a greater variability in your blood glucose level when you've been sleep deprived for over a 3-day period, the 3-day period following the night of sleep deprivation. So this is a separate paper published in 2020. And the kicker is I called this a fancy plot because why should the Italians and the Greeks have all the fun with naming? We need to have some fun too. So if you want, if it makes you hungry, even you can go to the literature and look up fancy plots, and you'll find them here. So anyways, what I just showed you here is also covered in an area called functional data analysis, where it's one step beyond a mixed effects model, where you model the entire function in a not necessarily linear way. And you're trying to estimate the parameters of those models and then ask, do they differ between these 2 groups? It's basically like an expanded mixed effects modeling approach. Okay, and then the last piece on this page, multi-level analyses and meta-analyses. These N of 1 data can be combined across people, because think about it. I've just drawn an analogy for you where one person is essentially their own study. We have methods to combine data across studies. They're called meta-analysis methods. And so in the N of 1 literature, they exist. They're frequently also called meta-analysis or series of N of 1 trials. And that's the way that we combine that data. It's directly analogous to meta-analyses. Okay, let's see, question here. How many hours of sleep did you deprive yourself? Do you have comparable data of its effect for different number of hours of sleep deprivation? Yes, so for sleep deprivation, we limited our sleep to 4 hours or less. And for each person, we didn't define in the protocol how to enforce it, but my colleague used an alarm, like multiple alarms, to make sure they only slept 4 hours on those nights. And then the other baseline nights were more than 4 hours. Your natural sleep, that was more than 4 hours. Or perhaps if you woke up, you made sure you got more sleep that same night. A particular time of night for experiment. Ooh, that's a great question. Time of night, we did, I don't recall off the top of my head what that time of night was. I will say that I believe for this person, it was fairly, not invariable, but it was generally around the same time of night. But it's a good question to look at because that is a variable you could put in the model, time of night, when you fall asleep. I don't recall if we did include that, so I'd have to look at the paper again. Comparable data of its effect for different number of hours of sleep deprivation. Yes, for data comparisons, I don't think we spent a lot of time on it, comparing it to. We did compare it to other data in the literature. I don't recall what those comparisons were. Because we also had a survey outcome for this paper. So we had the blood glucose outcomes, but also affect, so your mood, where we filled out a survey once or twice a day for what our mood was like. Good questions. Okay, and I'm getting close to time here. Yeah, some of the work that some folks in the space are doing. I used to work at a company called Avidation. They and the University of Southern California and the Rand Institute are now running this project. They may have finished by now, but this is part of a bigger project called American Life in Real Time, where they track intensive longitudinal data like this using a combination of surveys and sensors, and maybe even lab values. I started a newsletter for this, as mentioned in my intro. It's called Stats of One, and you can go to the website here. We also have a podcast if you want to learn more about these types of designs and what they're useful for. These are generally non-technical or very lightly technical blog posts and episodes. They're meant to be an intro to get you interested. Our mission is to promote the expanded use of these types of designs and other individual focused approaches. And then the vision is that we'll unite and synergize all of these types of idiographic or individual focused data collection and analysis procedures across the health disciplines. The field is, I'm trying to coin the term isometry. It's from Isa, right? So again, it's important for me to represent Filipino culture, Philippine culture, and I try to get into the literature when I can with these things. Okay, so this has been getting some attention. Stats of One was actually featured in a Forbes piece on health innovation, as well as a Fortune piece. So it's good to see that there's some attention from even the health business world on these designs being impactful. I was fortunate enough to attend this Fortune conference called Brainstorm Health. You had speakers like Vivek Murthy, who is the Surgeon General of the US. Chelsea Clinton was there. The CEOs of various pharma companies were there. And it was a great space to tell people about these designs because they're not widely known, but they really should be because we have all these data now that can be analyzed in a more meaningful way for each person, right? Not just an average across people. And that's it. So that is my talk. Before we cut to questions, I'll leave you with a few quotes. Oh, and then I'm involved with the DEI group at the ASA. If you ever want to check us out, happy to talk about that. The last quotes are, "I am large, I contain multitudes," by Walt Whitman, multiple time points. But what is contemporary technology, if not a mechanism for the containment of multitudes? By Taylor Fang, at the time a high school student, wrote this in the MIT Review website. Virginia Woolf wrote that a self that goes on changing is a self that goes on living. And my good colleague, wonderful person, Patrick Onkana, wrote, "Even if one is a single case researcher, it should not imply that one is a lonely researcher." So please join us at Stanson 1. Here are the slides.
Okay. All right. Thank you very much, Eric. Very interesting. And I think this is really important because this goes towards personalized medicine and how we can't just give one treatment to everybody, but you have to consider each individual, the genetic makeup and all that. I see that Al Sarafika has raised his hand. Al, can you show your face?
Okay. Well, thank you, Eric, for taking the time to present to the group. My name is Al. I'm a chairman of the board for PAASE. I'm based in the Philippines for the last 12 years as a balik scientist and helping the ecosystem for tech transfer and commercialization in the Philippines. I was in the US for 25 years doing medical device research and product development and making medical implants. So just to give you some relevance where we are in the Philippines, I'm a member of the National Academy of Science as well, and our recent discussion on omic technologies, the omics technology, indeed, as Marge mentioned, is leading towards precision medicine. And one of the key areas that we wanted to focus on is on on omics matching with some of the treatments, specifically for the top disease killers in the Philippines, one of them being cardiovascular diseases. So clearly, the more relevant study for me would be around the use of hypertension, anti-hypertension drugs, focused on its effect on the genome of type of the Filipinos. Because according to Dr. Roddy C., he said that we have to match it the same way they match it for breast cancer with the treatment versus its genomic profile. So looks like, at least from a surface analysis, 1/3 of the types of anti-hypertensive drugs only work at 1/3 at a time. So if we can narrow down that variability by matching them, we might achieve an 85% success rate, like in breast cancer treatment below type 2, I think, or stage 2 or stage 3. So how do we then apply the N of 1 methodology that we just described in order to effect, especially your treatment methods? Because the way I've done clinical trials and randomized clinical trials for wound care before, and for me, I'm trying to match it now with the current need. If I were a patient, like the way you did it for yourself, I have hypertension, but I'm exercising, so I don't need drugs yet. But if I were to go through the process, I can have my genomic testing and then test the 3 types of beta blockers and all of the other drugs for hypertension. Then how do you kind of design the study for me as an N of 1? So it's a very relevant question. I mean, I'm not only a questioner, but I'm also the subject. Just like, I like the way you did it. Perfect. Thank you.
Yeah, wonderful question. Thank you. And I appreciate your background on this too. It's always good to get people from different backgrounds eyes on this. So with genetics and omics, the way these fit in there, full transparency, I haven't pushed into that area of N of 1s. I do have a few colleagues who work there, but the way I understand it is you could use your omics data, for example, to help. They're typically used in precision medicine as a top-down approach, right? and it's called precision medicine, but essentially you're still fitting a population level model. It's just you have a lot of covariates. And so the idea is, logically, if you take those covariates to not quite infinity, but as much as you can go, only one person eventually is going to have all those covariates. And that's where you meet from the bottom up, this N of 1 design. The bottom up approach here is we're going to start with you and see what's working for you. But you can pair them, where we use omics to really narrow down the subgroups, right? And then now you have a good idea for each subgroup, which beta blocker works best for which. Within that subgroup, now you can use N of 1 designs to see which is working for a given patient. And in fact, that's how these methods historically have been used. They haven't been used many places, but in Australia, for at least a few decades, the government funded some of this work for clinicians. It's a clinical service. So instead of your doctor saying, hey, try this for a week, see how you feel, now try this, whatever, they just make it a little more rigorous and they do a randomization, and that's it. So that's where these fit into that pipeline. It's not so much on the research side, it's on the treatment. Once you have the drugs already, then let's use this design to really tailor it for you, what's working. It's more of a tailoring approach, yeah.
Thank you. I think that's probably talk you about moving forward if we have implemented in the Philippines in terms of going through a more genomic surveillance study. We're hoping that the government, at least Department of Science, would be receptive to such study. But thank you again for making yourself available to the interface of scientists and engineers. Thank you.
I think there'll be a lot of longitudinal studies to be taken once you take the medicine. When I started taking this high blood medicine, no, it was sugar, lowered the sugar. You measure the sugar at the beginning, and then you give the medicine, and you measure at the end. So after between doctor's visits, I asked my doctor, can you do a blood test for me to see if my sugar went down? He goes, oh, we don't do that. I'm like, I'm a scientist. I want to know the measurement before the intervention and then what happens after the intervention to see that it really worked. And is it worth it taking this medicine? I guess that would be the way to go. That was my N of 1. Okay, so here's a question from Dr. Asuncion Raimundo. Can you explain again how the results of N of 1 can be statistically acceptable? It can be equivalent to the case studies, but those are not considered statistically significant.
Yes, great question. Thank you, Dr. Raimundo. I get that a lot. The way it works with N of 1s is the fundamental question that's being asked is different. The target population in these studies is just that one person. It's the same as the target population of a time series. And so when you have that, just like you would with a group, for statistical significance, you have a sample size question. How many measurements do I have to take to be sure that there really is a difference in my outcome between these two conditions? So it will come back to kind of classical sample size questions, in particular for time series data. So the idea for N of 1s is how much does your findings from your own N of 1 study generalize to yourself over all of the hypothetical times you can undergo these two different conditions? That's the analog to the population level, which is from my sample of people, how many people do I need to be able to generalize to the entire target population? Now, that's answer 1 of 2. There's 2 answers. The second is, I also get the question, okay, that's great, Eric. How can we generalize this though? Like, what's generalizable about this method then? How is it useful? What's generalizable is the design itself. So for example, I can set up a study that has one arm of the study is classic RCT, drug A, drug B. The other arm is, we have one more arm, and it's an N of 1, a series of N of 1 trials for each person that will see what the difference in effect is and then adjust to a next stage N of 1. And so there, what happens is the NF1 approach will win over the RCT approach if, for example, half your people are helped by coffee with their migraines and half the people are hurt. The RCT will find zero average effect, whereas the NF1 approach will find all these different effects for different people, which is perfectly valid because that's essentially that's what you want in the clinic. You want it for each person. So the generalizable part is the procedure. It's kind of it's a little bit analogous to confidence intervals. No single confidence interval gives you a probability. You're confident in the procedure of the confidence interval. The procedure itself is what gives you confidence, not any particular calculation. So I hope that helps.
Yeah, we have another question from Dr. Billy Cablion.
Oh, yes, ma'am. Good evening. Okay. I will confess to you, Dr. Daza, that the topic presented this evening is very dense to my intellect. And I had to do a little reading this afternoon just to be prepared that I could understand what you would be talking about. But I have a practical question. There are wearables, and I think you mentioned Fitbit, and I think the Apple. And then our vice president mentioned about the disease diabetes. You know, the menu for treating diabetes is there's a whole permutation of how much insulin, how much metformin, and when do you take it, and all of that. So my question is that Apple has invested and touts that the Apple Watch will make you live forever if you just wear the Apple Watch. Now, is there any data really, trying to understand what you just presented tonight, that over a period of time, if you wear your Apple Watch, that it can tell you what your optimum anti-diabetic medicine should be? Is there data that says that, or is it just kind of advertisement that we can measure your blood sugar? If you keep your blood sugar down, you're going to live forever. So that is my practical question.
Yes, thank you, Dr. Cablion. It is a practical and very top important question, right? The short answer is I myself don't know that area that well, how valid these device measurements are. There is a body of work on it. What I can say is there are organizations, at least in the US, that have now for maybe 5 to 10 years at least been coordinating between regulatory bodies like FDA and industry, especially these tech people. So I'm interested in the potential, but I'm also very skeptical, right, of how well these devices capture what they say they capture. And there are groups now that work to bridge those two gaps. So what I mean by that is FDA needs endpoints in their clinical trials if you want to say your Apple Watch can really profile your diabetes, right? Okay, you're going to claim that. Now you have to go through FDA. You have to go through FDA. How do you define your endpoint, your outcome? Oh, you don't have that. You can't claim that then. But there are groups now that are starting to really push the tech companies to say, this is what they need. You understand why this is very important, right? You can't just sell this product. This is a life or death thing for many people. So completely understand. That is my hand-wavy answer. happy to follow up too afterwards. I'm involved with this group, so how to validate, devices and all that.
Okay. Do we have any other questions? Methods or applications? Feb, is there questions in the live? I'm trying to see.
Check.
Yeah, okay. No? Okay. If there are no other questions, I guess we can thank Eric for this very here's one more. Hi, sir. How about the body fat percentile calculations?
Oh, that's another one. That's it. Man, y'all are hard today. That's another device question, which I am not like I don't know that area really at all for how how reliable a lot of these measurements are. The examples I showed you, we picked also out of convenience. My co-author is a sleep physician, and so he's guided me to say, this Fitbit for sleep duration, it's good enough. We're not going to make medical claims off it. It's a toy example to demonstrate a statistical method, but it's good enough for this. And in fact, what I showed you is the opposite direction of what we're publishing, because he said it's in this, Dr. Caballero, to your point, what's useful. My physician friend said it's more useful for my patients to ask, is there an effect of my physical activity on my sleep? Because I can change my physical activity on a given day much easier than I can change my sleep. Like if I have work, I can't move my sleep window if I get late sleep, but I can choose to go to the gym or go on a run in an easier way. So actually the final paper, you'll see it'll be flipped, the effect of walking speed on sleep.
Okay. Yeah, I was just going to comment that today I was reviewing an animal protocol for sleep-deprived mice, pregnancy and baby mice, and how they are sleep-deprived. And we actually use a prod so they don't go to sleep, just keeps waking them up. There's a rod at the bottom that keeps going so that they stay, they're sleep-deprived for certain times of the day, for certain times. So that's very interesting. Okay, so that was mouse work, not robots. All right, I'm a mouse person, I suppose. Okay, so I see that there are no other questions now. All right, so please join me in thanking Dr. Eric Daza. I hope we can bring you again in the future with some of your results. They're very interesting and how applicable they are. And so, Eric, we have a certificate of appreciation for you. The certificate of appreciation is presented to Dr. Eric J. Daza, Eric J. That's what we call you, right? DrPH MPS, for being our speaker at the Philippine American Academy of Science and Engineering webinar titled Discovering Your Own Health Behavior Causal Effects Using Wearables and Apps, held on September 6, 2024. Presented this day, September 6, 2024, with our deepest gratitude, signed by our president, Dr. Gladys Cherise Completo, president for 2024-26, Philippine American Academy of Science. So everyone, please join me in thanking Eric for this seminar, and hope to see you next week. We have in 2 weeks' time. If you guys have noticed, we have been doing our seminars bi-weekly so that you're not very overwhelmed, but we're always holding them on Friday morning in the Philippines at 8:30 a.m., which is Thursday evening in the United States at 8:30 p.m. And so if you're looking for seminars, look for those days, and that's when we have scheduled them so that you will not be lost in the internet space trying to find them. And so our next seminar will be by Dr. Sherry Pagsuyuin from University of Massachusetts. It will be on applications of wastewater-based epidemiology for long-term drug use surveillance. And again, this is very timely. I just had a seminar today talking about this entire thing. The next one will happen on October 18th, and this will be presented by Dr. Manuel Vidal. the development of a placenta on a chip model to evaluate the effects of endocrine disrupting compounds in inducing acute placental dysfunction. So these are seminars that are scheduled, and please keep on the lookout. We have more seminars coming out till the end of the year. And so again, it's always on Thursdays in the US and Friday mornings in the Philippines. Okay. So thank you, Eric, and thank you everyone for coming. We truly appreciate your attendance. And to all those who are on the Facebook Live, thank you as well. And Eric, this is recorded, so it'll be watched over and over again. All right. Thank you. All right. Good morning and good night, everyone. Okay.
Bye. Thank you.
Okay. Thank you, Ma'am Shoni.